Professor Siva Sharma.
Yeah, good morning, everyone. Thank you, Professor Ramki. Thank you, Professor Kajari. So welcome to the first session of the workshop. So we have two talks in this session about the early story of the Higgs boson and its discovery. So before we start, let me quickly introduce our first speaker, Professor Rohini Godbolt. She is superannuated from the Indian Institute of Science, Bangalore, and she is now an honorary professor at the Center of Energy Physics there. She has worked extensively on different aspects of particle physics phenomenology over past 4 decades, and her expertise and interest encompass the Higgs physics as well as the beyond standard model search probes at the colliders. She is an elected fellow of all the 3 science academies of India, as well as the Third World Academy of Sciences. Among her long list of awards and honors, the prestigious Padma Shri of the Government of India, and also the French National Order Merit of she received in last January. So let's move ahead and hear from Professor Godbolt about the early story of the Higgs boson. So Rohini, can you please share your slides?
Yes, so thank you very much. First, let me express my happiness at this entire effort that Kajari and the team have put in to organize this celebration. And thanks for inviting me to talk about the early history. For somebody who began her graduate studies in 1974, which was the year when the gauge theories of weak interactions officially were kind of proved, first proofs were obtained through the discovery of J psi, and who was actually present at CERN on the day the Higgs discovery was announced. Actually, I was present along with Seema at CERN on that day, on 4th of July. So for me personally, it's also encompasses to some extent a personal journey. So thanks, Kajari, for asking me to talk about this. So Kajari first told me, tell us why we need the Higgs boson. So in that sense, I thought, there is so much known, even on, if you type Google and Higgs boson, that I can finish my talk in one line. But then those of you who know me, I can never finish my talk in one line. So I decided that I'm going to make my talk add some more meat to it, other than why do we need the Higgs boson? And so this is the plan of my talk. So I will really begin at the beginning, that is beginning of the story, which is the fact as to why do we need a massive Doped boson. Then the second part of begin at the beginning is the spontaneous symmetry breaking. And for most of the audience, which most likely consists of younger people, they may not know that spontaneous symmetry breaking was not introduced to solve the problems, ills of the electroweak theory, but there were very brilliant people like Steven Weinberg who combined the spontaneous symmetry breaking with the other ill of the electroweak theory, namely the massive W, and they came up with a wonderful model, which we call the standard model, which was combination of 1 and 2. And that involved the constructing a Higgs, and that Higgs has certain properties in the context of the standard model. So I will tell you what we knew and what we didn't right from the paper, which is called the model of leptons, which was written by Steven Weinberg. And then I would actually go to the 2 points as to how did the theory and the experiment analysis of precision measurements together narrowed down the place where we would finally find the Higgs boson. And that would end there. I would end up with what was the landscape of the Higgs that we wanted to look for, or that we thought the Higgs should lie in on the eve of the Higgs discovery, that is December, or actually even December 2011 to March 2012. And somewhere where I will only weave in only my early involvement of my own in the story. So I am going to actually dedicate this talk to my PhD supervisor, Jack Smith, whose supervisor for his master's thesis was Peter Higgs. So my own earliest connection with the Higgs started when I started doing PhD with Jack Smith in 1974. All right. I just wanted to kind of say one small thing that yes, we are celebrating 10 years of the Higgs, but I would like to add the word Higgs discovery. That is, these are the 10 years that the particle physics community has been living with a Higgs particle that was seen in the experiment. But I think it's been living for more than half a century with the idea of the Higgs, when, as the saying goes, the Higgs was a twinkle in the mother's eye, namely 1967. So let's begin at the beginning. For weak interactions, I would say the beginning was the V minus A theory, which was put forward by the Indian physicist Sudarshan with his supervisor Marshak in his PhD thesis. And at the same time, actually a little later, by Feynman and Gell-Mann. And what they did show was that the 4 fermion Hamiltonian of beta decay can be written simply as the product of neutron-proton current times the completely left-handed electron-neutrino current, and of course the Hermitian conjugate. For the case of muon decay, the Hamiltonian looks very similar, except that it looks even more symmetric because Ca mod of Ca by Cv for the muon is 1. Now, this was really the V minus A theory. So in fact, what the V minus A theory said, and here I have more or less copied, slightly changing the notation from the Sudarshan Marshak paper, apart from the 2 equal to signs that have come there as a typo. So what did they say is that the 4 fermion effective interaction is written as the product of 2 currents, which all involve only left-handed fermions. That is actually the major point of this. And that meant that the currents that were involved here were either vector or axial vector bilinears that could be constructed out of these 2 fermions. But actually, this was, in principle, you could have constructed a much bigger jungle here. And out of all the possible terms that could have been there, the nature told us that it is only product of this vector V minus A and V minus A current that describes the weak interactions that are observed in nature. And this fact that it's a vector or axial vector current meant that this point-like 4 fermion interaction can be thought of as being due to an exchange of a spin 1 particle, the weak boson. In fact, this idea was introduced by Schwinger even before the V minus A theory, because already by the time this current-current interaction was established, this was 1957, Gage's theory of electromagnetic interaction was proven, and Schwinger, of course, had played an important part, and he would always talk in terms of currents, and therefore he introduced that this axial vector current vector and axial vector current combination would be due to indicating the interaction of a weak boson, and that's why he called it a W boson. So in fact, when Sudarshan and Marshak wrote this paper, they mentioned that this would, their current Lagrangian or Hamiltonian would very nicely fit in with the ideas of Schwinger. So the extension of known QED, which was there in 1950, as I said, in 50s already. So anticipating Gage theory here, I am writing down the extension of the known QED to the weak interaction. And this is really what was proposed by Schwinger. But of course, in nature, we were seeing only point interactions, whereas if it was due to an exchange of a W boson, like here, because of this interaction vertex, the diagram for which we describe, for example, muon decay or in electron-neutrino, muon-neutrino interaction would have looked like this. But on the other hand, when at low energies, if the mass of the W was very large compared to the energies that are available, then it would have looked really like a 4 fermion interaction. And this 4 fermion interaction is what I have written here. So therefore, this is how the weak interaction Hamiltonian describes, which was a point interaction, can be thought of as being due to an exchange of a W boson. And that was the reason why I said that the V minus A interaction was the beginning. Okay. Now, if what happens is that one uses this 4 fermion interaction and calculates the cross section, because this is nu mu. This can be used to calculate nu mu to E minus going to mu minus nu E. And then what you find, that was the first problem with the Fermi theory, that the cross section rises with the energy. This S here is 2 times mass of the electron times the energy of the neutrino. So as the energy of the neutrino increases, this cross section increases. So what? So what is the problem is that if you now work out the partial wave amplitudes, you find that this means that the cross section will violate unitarity. That is, the scattering amplitude will have a magnitude which is bigger than 1 for energies which are, sorry, this should be greater than, for S greater than 4 root 2 pi GF inverse, this should actually will violate unitarity. So this means that S should be less than 4 root 2 pi GF inverse, and that would mean that MW must be less than 300 GeV, because then somewhere below that energy, the finite mass of the W will actually then tame this bad high energy behavior. There will be a 1 over Q square minus MW square, and Q square will be related to energy. And this way we find that the mass of the W should be less than, namely, basically 300 GeV. It cannot be infinite, it is finite. So for a massive W, unitarity for this cross section will be preserved. Now, so the problem of bad high energy behavior of the point-like theory was actually cured when we introduced a massive W boson, that is, which was introduced by Schwinger, in fact. Now, however, it's like a tarpaulin. You put it down in one place, it comes up in another. So as soon as you solve the problem by introducing a massive W boson, now if you go ahead and say that I can, now W is a real particle, I have actually this vertex, nu bar. So I can actually see how I can produce, this is a current vertex with a nu and a E bar, E minus. So it contributes to a process like nu bar going to W plus W minus. And now when you calculate these amplitudes, you find that these amplitudes violate unitarity at high energies. When neutrinos, again, this is a Gedanken experiment, you don't really have to have the high energy neutrino beams, but the fact that this process will violate unitarity says that this is a sick theory. And that is happening because of the longitudinal degrees of freedom of the W, which the W has only because it has a finite mass. In fact, Glashow in 1961, I think, noticed that if we think of a gauge theory, which is based on a SU2L cross U1 gauge group, this amplitude will actually become well behaved. I will come to that later in my talk. But now the problem is, there is another problem with gauge theories when the gauge bosons are massive, and that has to do with the fact that the gauge theories with massive gauge bosons are not gauge invariant. So what good are gauge theories which are not gauge invariant? In fact, that makes them non-renormalizable. If the finite mass of the W makes them non-renormalizable because they're no longer gauge invariant. If they're not gauge invariant, the gauge invariance cannot help us to make them renormalizable. If they're not renormalizable, we cannot compute anything. So it's a complete chaos. As I said, QED and as a gauge theory was extremely well understood at this time and established. Yang and Mills had already put forward the non-abelian gauge theories, which means as a theoretical construct, constructing a gauge theory of W plus W minus was possible. But the gauge theories of weak interactions, as I said, were not possible because we had proved explicitly that the W boson must have a non-zero mass. And if it has a non-zero mass, the theory that Yang and Mills had put forward could not be used because that was only a gauge invariant theory. So frankly, nobody had an idea how to sort out this problem. And in fact, I think nobody other than the inventors of the standard model were thinking of weak interactions as gauge theories. So let's just understand that by this time. A very simultaneous development which was happening in the world of particle physics, theoretical particle physics, was understanding of the symmetries. And this was happening in the context of strong interaction. And what was seen at that time, that nature abounded with symmetries, many of which were approximate symmetries. Isospin symmetry, Flavor SU3. I think these words make sense to perhaps people who even now who study particle physics, because we do still talk about these things in our particle physics discussions. So what was other point was that for here I already showed you that for pure leptonic currents, CV was equal to CA, that is the mod CV minus CA was 1. But for currents involving the neutron and the proton, CA and CV, CA by CV was different from 1. It was actually 1.25. So which means that there was some difference in the neutron proton current compared to the muon neutrino current, because muon neutrino current had the CA over CV equal to 1, and the fact that you are now talking of proton and neutron currents, that somehow dressed the structure, the strong interactions of the neutrons and protons, dressed this axial vector part of the current. And that was actually the observation. And this observation was made, in fact, by Feynman and Gell-Mann. So I think that was actually the important part of the Feynman and Gell-Mann work. So they talked of this, they understood that CV by CA being slightly different from 1 for beta decays, that it's perhaps the effect of strong interactions, and the strong interactions do not conserve axial vector current, they conserve the vector current, and therefore the vector coupling remained unchanged that from that of the muon. However, the axial vector coupling changed, got renormalized. And this meant that there is a breaking of the chiral symmetry, because when I change left to right, if this happens, then strong interactions break chiral symmetry. So, but the deviation was 1.25. From 1, it went to 0.25, which means chiral symmetries were broken, but not in a huge manner. So people started discussing how such symmetries could be described. And in fact, in the meanwhile, Goldberger and Tremann proved very important rule by which they showed that the magnitude of CA could be understood if the divergence of the axial vector current was proportional to the pi on the field. Now, this was, there was no need for this to happen. But if you assume this, they could prove the experimental observation that CA by CV was 1.25. Around this time, as I said, because of this small breaking of the chiral symmetry, people had started thinking about spontaneous breaking of a symmetry. And at that time, as Weinberg puts, so I have it on good authority, they were confused. They thought that if the symmetry is spontaneously broken, it will be soft, broken softly. But in fact, the whole essence of spontaneous breaking of a symmetry is that the vacuum is only the vacuum, which does not exhibit the symmetries of the Lagrangian, but the Lagrangian is still very much symmetric under the transformation that you are looking at. So this idea of strong SSB was in fact introduced, as I said, in the context of strong interactions. And Weinberg, Salam, and Goldstone proved a very path-breaking theorem, which many of us always remember it as Goldstone's theorem, but actually Goldstone made a conjecture. And I reproduced the first lines of the abstract. It's a wonderful, smart, I think it's a wonderful proof, example of a beautiful theoretical paper. So the proof is, some proofs are presented of Goldstone's conjecture that if there is a continuous symmetry transformation under which the Lagrangian is invariant, then one of the two things must happen. Either the vacuum state is also invariant under the transformation, in which case the symmetry is not spontaneously broken, or if the vacuum state is not invariant under the transformations, that means symmetry is spontaneously broken, then there must exist spinless particles with zero mass. Now, this was the famous Goldstone theorem, which said that if there is a spontaneous breaking of a continuous symmetry, there must exist a massless scalar, spinless particle. And since there were no massless, spinless particles were known to exist, as Kajari told us, Higgs was the first scalar that we ever found out. So no fundamental massless, spinless scalar was known. So clearly this theorem in 1962 put paid to the idea of spontaneous symmetry breaking in field theory, so people thought. Now, there was a major difference between the symmetries that people were looking at earlier. Nambo was the first one who made sense of the whole thing by pointing out that one can justify the Goldberger-Tremann relationship by understanding that the chiral symmetry of the strong interaction is spontaneously broken. But then people would say, haha, but where is the massless boson? But then came Goldstone's, Nambu's wonderful insight, where he showed some very beautiful, intricate calculations. And he said that if the symmetry were an exact symmetry, that is the chiral symmetry was an exact symmetry, pion would be massless. And in that limit, nucleons would also be massless. But we know nucleons are not massless. We know pi, and therefore the chiral symmetry is not exact. We have then because it is almost exact, but not quite exact, we have an almost massless Goldstone boson, which they call the pseudo Goldstone boson. This terminology was also introduced by Weinberg. So this actually clarified the implications of the SSB for strong interactions. And the important lesson that one learned from here is that the spontaneously broken symmetry, though broken by the vacuum, in this case, the nucleons have masses, it was visible in the interaction of the Goldstone boson, in this case, the pion. Actually, Anderson was one more person who had understood this deep intricacies of spontaneous symmetry breaking. And he actually is the first one to apply it in the non-relativistic context for the Yang-Mills interactions. And there he showed that including the Yang-Mills interaction, the problem with the zero mass Goldstone excitations actually vanished in the context of the superconductivity and many other examples that he gave. So the abstract of this paper of 1963 is also very beautiful. So I produced few lines of this. It is also shown that the Schwinger's criterion that the vector field with mass equal to 0 implies that the matter spectrum before including the Yang-Mills interaction contains a m equal to 0 excitation, which means that if the vector field has to have mass non-zero, then the matter spectrum before including the Yang-Mills interaction must have m equal to 0. But that the example of the superconductivity then indicates that the physical spectrum need not contain this m equal to 0 excitation. And then he ends by saying that some comments on the relationship between these ideas and the zero mass difficulties theories with broken symmetries are given. So he understood that this will have implications for the field theories and for which are relativistically invariant, and this non-relativistic formulation obviously was not enough. But that is where, so now in principle what we have is we have two theoretical ideas. One idea that the local gauge invariance of a theory requires massless gauge bosons. So how can we have massive gauge bosons and still have a Lagrangian that respects this symmetry? And that spontaneous breaking of a continuous symmetry would achieve that, because Lagrangian would respect symmetry and the amplitudes will not, but at the same time the ground state will not. But if we do that, then there is always a massless scalar in the theory. So that's where Peter Higgs, as well as Anglais and Braud separately in 1964, came up with this idea that let's marry the spontaneous symmetry breaking with a local gauge theory, because earlier all the discussions were about spontaneous symmetry breaking in a global symmetry. So when you combine it with a local gauge symmetry, then we find that, I misspoke. The earlier it was a continuous symmetry, but it was not a gauge symmetry. There was no gauge theory. Here you couple it with a gauge field. And then what happens is that the massless Goldstone boson disappears from the spectrum and a massive gauge boson appears in its place, exactly like what Anderson said. What Anderson had done in the non-relativistic context, these people showed can be done in the relativistic context. But actually, I must tell you that neither Higgs nor Anglais nor Braud were worrying about the electroweak interactions. They were worried about strong interactions. They were wanting to use SSB for strong interactions. And they, as a matter of fact, Higgs goes on record saying that had I known this, we could have easily applied it, but they simply didn't know this. And they were only interested, as I said, to look at how a massless Goldstone boson, which must exist in a theory with SSB, can be removed from the physical spectrum, since physically we don't see a massless Goldstone boson. And that is what they showed, that if you marry SSB with a local gauge theory, world will be fine. There are no massless excitations hanging around. And you got another good thing. You got a local gauge theory which can have a massive gauge boson. So you start with a Lagrangian, which is invariant under a local gauge transformation with a complex scalar field phi, and with the wrong sign for the quadratic term, which you can see here. And the physical vacuum will then correspond to the case where the field achieves a finite non-zero vacuum expectation value. So this is the minimum of this potential, and the vacuum will settle in one of these many minima. Okay, and you can take any value, any phase, and that will be the minimum. Vacuum will be that any one direction, any one point. And now if you do the algebra, you then find that the MA what happens is that if you write this and you write d mu phi dagger d mu phi, where phi achieves a vacuum expectation value, lo and behold, suddenly the mass term MA equal to GV arises from this d mu phi dagger phi dagger. It is this term which contains MA square A square term, and on top of it there is a physical scalar which has a mass m eta equal to square root 2 times mu. Now here I must tell you that you begin with a complex scalar, which means you have two scalar degrees of freedom, and what you are left with is one scalar degree of freedom and one massive vector degree of freedom. This is more or less in toto from the Higgs paper. So in this example, I already said this, you start with a complex scalar and the massless gauge boson. The mass term for the scalar field is of the wrong sign. So this is not a propagating scalar field. And after spontaneous symmetry breaking, you, lo and behold, you have a propagating scalar field, a massive propagating vector field. And in general, the number of scalars that will come out at the end of the day after spontaneous symmetry breaking, physical scalars, will depend on the pattern of the symmetry breaking. And I will come to that later, because obviously we know that there exists one massless gauge boson in nature, the photon, whose gauge theory was already known. So whatever final theory we write, we will have to make sure that the symmetry corresponding to electromagnetism is not broken, because that gauge symmetry is exact. So as I already said, neither of the proponents of the SSB mechanism knew about the issue with electroweak interactions, and they did not apply this solution to the problem. They had the solution. But Weinberg and Salam independently noticed that they had been worrying about spontaneous symmetry breaking, and they actually therefore noticed it very nicely. And Weinberg writes in his memories that he realized suddenly that he is trying to apply SSB to a wrong problem. He is trying to apply it to a strong interaction, whereas the problem which he himself had noticed was sitting there, and there is a beautiful solution. So both of them actually imagine that since the non-zero mass of the gauge boson is generated in a gauge invariant manner, the gauge symmetry would actually guarantee a good high energy behavior. They didn't prove it, in fact. So this is the famous model of Lepton's paper, which I call, the beginnings of a gauge theory. And that is my starting the beginning, so to say. So this is the model of Lepton's. So this is the marriage of two beginnings. Marriage of the massive W boson, the idea of the massive W boson, and the marriage of spontaneous symmetry breaking ideas in a gauge theory. So here he goes and says he's written is a model of leptons. He didn't believe in quarks at that time. That's why he wrote it only as model of leptons. And then he said that with the intermediate bosons that presumably mediate weak interactions. So this was Schwinger's presumable mediators of the weak interactions. It's actually a wonderful paper, I find. What could be more natural than to unite these spin 1 bosons into a multiplet of gauge fields? That's where he is now trying to write down his idea of unification. And the obvious difficulty in this synthesis is that the masses of the photon and the intermediate boson, there is a big difference, and also there is a big difference in the couplings. We might hope to understand these differences by imagining that the symmetric relations between the weak and electromagnetic interactions are exact symmetries of the Lagrangian, but are broken by the vacuum. So he right in the first paragraph says he is using the spontaneous symmetry breaking. And then he goes on to discuss, then he says this raises the specter of unwarranted massless Goldstone bosons, which they themselves had pointed out in their 1960 paper. And then he says, this note will describe a model in which the symmetry between the electromagnetic and weak interaction is spontaneously broken, but in which the Goldstone bosons are avoided by introducing the photon and the intermediate fields as gauge fields. Everything that I said so far is here in this first paragraph, and the entirety of standard model ideas are here in this one paragraph. And then he ends with the first paragraph by saying the model may be renormalizable. They didn't know that, but they hoped that because the symmetry is spontaneously broken, the Lagrangian is invariant, the model may be renormalizable. And this Lagrangian is something that all of us write all the time, and this is the Lagrangian from this paper, okay? And here I want you to notice, for example, there are these interaction terms between the leptons and gauge bosons, and we are going to come to that a little bit later. And also there should be a Yukawa term. I think I have not copied it correctly. It has gone outside the screen, so I will mention that later. Okay.
Rohini,
So in
can I interrupt?
Yeah.
Since there are many students connected, I just wanted to ask if any questions already, if you don't mind.
Okay, please.
I saw one hand was raised sometimes ago, Ram.
I think he has vanished.
Okay. If
Okay,
any other
thanks.
questions, then please go ahead. Otherwise, we continue. Yes, he is back.
Yeah.
Yes, Ram, please go ahead.
Hello?
Ram, can you please unmute and ask your question?
Either he cannot unmute or whatever.
I think he is unmuted, but we can't hear him.
Maybe you type your question in chat, maybe we take it at the end. Okay?
Yeah, then we take it at the end.
We take it.
Okay, Rohini, I have one question. I am not a student.
Yes, Govinda.
Just actually, sometimes back, I was just looking some of the Nobel lectures.
Yeah.
And both Weinberg and Weinberg and Higgs, both of their Nobel lectures, they mentioned, Weinberg mentioned that what I was talking, Higgs did not understood. Even Higgs, when he taught in the Nobel lecture, he says that while I was talking at that time, Weinberg did not understood. So what is that? Do you know anything beyond this? This is just
I actually don't know this, but as I said, I know this for sure. I was going to actually put that quotation of the Higgs, that Higgs had said that I did not know about the electroweak theory. That much I know. That he didn't know the problem of electroweak theory is a statement by Higgs, which is written in a lecture. But the other part that Higgs said that Weinberg didn't understand Higgs, I don't know that. All I know is that actually, maybe as I come, I have some specific statement to make. So why don't you wait till then? Okay.
So until this point, the whole idea started essentially to explain the strong force as the exchange force, right? Using the pions.
Exactly. And only when Weinberg applied it to electroweak theory, that this is now a specific massless excitation. So that's why I'm actually still showing you that Glashow put forward the idea of electroweak unification in 1961 and his W's and Z's were going to be massive, but he didn't really had a model for how those masses are created. So this was much before Higgs, Angler, Broad papers, and Glashow simply didn't at this point care how the mass was generated for the W's and the Z's. And Govinda, I'm sorry, but we will discuss this, take this offline, okay?
Okay.
So I will anyway say a few things as we go along and see if your question gets answered. So,
hello, madam, can you hear me now?
Yeah.
Yeah. So I had the question on the slide where you mentioned that the axial vector and vector like product is the only one that's possible. So my question is, does this fact come purely from experiment, or
this comes frankly, it came because it's very amusing since you asked this question. At the time this was put forward, there were 4 experimental results which were in contradiction with this form. And Sudarshan and Marshak put it forward by saying that this is a principle of chiral invariance. That means that the current should not change the chirality of the fermion involved in the current vertex. And then if you say that it should be chirality conserving, the only current that gets left over is vector or axial vector current. So in fact, I consider the paper of Sudarshan and Marsha to be very superior, because it is not just the encapsulation of an experimental observation, but they were led to it by an hypothesis of chiral invariance. And they in fact write a line in the paper that if any of these 4 facts, which are experimentally right now in contradiction with our hypothesis, are confirmed by future experiments, our hypothesis will have to be forgotten. I mean, I consider that as the biggest property of a theory paper. Okay. So for me, they extracted it from data, but they also had a principle guiding them. And Sudarshan and Marshak had this principle, whereas Feynman and Gell-Mann had the principle of 2-component neutrinos. That was related to the fact that you had almost massless neutrinos. So I would say that yes, they were driven by recognizing the importance of the handed fermions, that is chiral fermions. I hope, Ram, I have answered your question.
Thank you, ma'am.
Okay. So now Weinberg's model of leptons actually went beyond Glashow's 1961, sorry, this was a typo, beyond Glashow's 1961 paper. It was of course, just like Glashow, it was a unified description of electromagnetic and weak interaction together in a SU2L cross U1 theory with massive W and Z and massless photons. But both Weinberg and Salam used Higgs mechanism, which is going beyond Glashow. And therefore, in Salam and Weinberg model, there existed perforce, they had a model for masses, the model involved Higgs mechanism, and therefore they had one additional scalar. And the fact that they got only one additional scalar in their model was because they chose a doublet scalar field phi, which Weinberg says that I'm choosing it ad hoc. It is the minimal choice that is required to break SU2L cross U1Y to U1 electromagnetic. And as I said, the difference between Glashow's paper and Salam Weinberg's work is that this contained this additional scalar, the particle spectrum contained an additional scalar, and that is the Higgs boson whose decade we are celebrating in this conference today. So Weinberg and Salam, as I said, used the Higgs mechanism to make the massive gauge bosons consistent with gauge invariance. But actually, this was only one way of achieving it. It was not likely, but not necessarily probable that Weinberg's model was right, but still there would be no elementary Higgs scalar. That could have happened. And the 1967 papers had also shown that that is the windfall actually, and that is present in Weinberg's paper only, that you can get masses to the leptons from the Higgs mechanism in a gauge invariant way. And as a result of that, the choice of the representation to which this scalar phi belongs decides the couplings of the Higgs bosons with the fermions as well as with the gauge bosons. So the profile of the gauge boson, Higgs boson, now in the 1967 paper, it's completely determined in these ways. So what is not known in the paper and anywhere at that time, and to nobody, not just in the paper, was nobody knows anything in the model about the mass of the Higgs boson. It knows about the mass of the W, the mass of the Z, and the mass of the fermions in terms of some parameters of the model. And the mass of the Higgs boson was completely arbitrary, left free to hang. But the couplings to the gauge bosons in the fermions were actually known in terms of the other parameters of the standard model. So this is just a pictorial representation that you start before symmetry breaking. We had 4 massless gauge bosons, 8 degrees of freedom, 4 scalar fields, because we had doublets, complex doublets of the scalar. So 4 scalar fields, you do spontaneous symmetry breaking, considering unitary gauge, you find 3 massive, 1 massless gauge boson and one massive scalar boson. So now again you have 11 degrees of freedom plus what did I have to do? I did. Let's forget it. I have done something crazy here. The 3 or 9 plus 11. My calculation is going wrong, so we'll leave it right now. So I think I've typed something wrong. So the ratio of MW to MZ depended on mixing angle, and also to the representation to which the scalar phi depended. So for the choice of the doublet, you had rho equal to 1, and this rho here is being defined as the ratio of the charge current interaction to the neutral current interaction in terms of two observables. Actually, let me close this and see what I'm saying. Yeah, this is okay. This is, I was getting lost. I was not seeing my slide completely. This is the calculation I wanted to do. 8 plus 4 here are 12. Here there are 3 3s are 9. The 2 degrees of freedom of a photon, 3 degrees per massive gauge boson. These are 11 degrees of freedom, and the physical scalar, which is the 12th degree of freedom. So I'm happy I can still add. All right. So this was actually one of the predictions of the model. So let's see what were the predictions. It predicted new particles and new interactions. And one was the existence of the Z boson and the weak neutral currents with the relative strength of the charge and the neutral current interactions given by rho, which would be predicted to be 1 for the choice of the doublet. So if you saw rho equal to 1, then you know that doublet is a minimal extension is correct. And then it would predict one scalar for the simple choice of a single doublet. If I have 2 doublets, then I would have 5 scalars, which is what happens, for example, in supersymmetric theories or 2 Higgs doublet models, so on and so forth. So the existence of whether exists only one additional scalar or there exists more additional scalars depends really on the choice of the representation. And that's something that we can go on, and that will be discussed in the course of this conference. So the standard model Lagrangian consists of the proved gauge sector, the Yukawa sector, and the scalar sector. You break the symmetry spontaneously with mu square less than 0 for this choice of the Lagrangian in the term. And then the vacuum expectation value of the scalar field is 1 over root 2, 0V doublet. And the vacuum is clearly not symmetric because it has broken the SU2 symmetry, but the Lagrangian still is. And therefore, the scattering amplitudes are gauge invariant. And then one scalar degree of freedom is left. Now here I'm just writing the things for, earlier I wrote for U1 gauge symmetry. This is for SU2L cross U1 gauge symmetry, breaking to U1 electromagnetic. And what is important here to note that the V is defined in terms of these two parameters of the Lagrangian, but V itself is given in terms of the measured constant of muon decay. And the Lagrangian for the scalar is here, where mh square is defined to be 2 lambda V square. V is defined as a numerical value from the observed muon decay. However, lambda is an undetermined parameter, a free parameter. So in the standard model Lagrangian, the paper on theory of leptons gave mh square to be 2 lambda V square and said it's completely arbitrary. What is also important is that there are scalar interactions with each other, which in the final after spontaneous symmetry breaking, which also depend on the same lambda. So this lambda characterizes the scalar sector completely by itself, the self interaction and its mass, and it does not enter in the interaction of the Higgs with the other fermions or the other gauge bosons. And this is properties as J equal to 0, it is CP even, its hypercharge is Y equal to 1, and SU2L doublet. So the tree level couplings, HVV or HHVV and FF bar H, all are proportional to mass of the respective particles. And thus the Yukawa coupling of the Higgs is proportional to the measured mass of the fermion. The gauge boson coupling HVV is proportional to the mass of the V, and so is HHVV. And in terms of small v, which is known. Couplings to GG and gamma gamma are loop induced. And for example, here the gamma gamma can couple to a Higgs, which is neutral, through a W loop as well as through a heavy fermion loop. And similarly to the glue, coupling to the glues of the Higgs is also through a quark loop, because quarks are the only ones that carry strong charge and they can couple to the gluons. Here the fermions can be either the leptons or the quarks. And at the time when, for example, the whole idea, I will talk, okay, let me not jump ahead of myself. I will come back to this issue. So in the standard model, the contribution to the Higgs to gamma-gamma coupling is through the W and the top loops, simply because the remaining fermions are very light, and the coupling of the Higgs to the fermions in the standard model is proportional to the fermion mass, as a result of which the relevant contribution here comes only from the top loop. And for the HGG, it is only the top contribution, of course. And new particles beyond the standard model which contribute in the loops, and the contributions, the important point is that these contributions are non-decoupling. That is, as long as the mass is generated by the Higgs mechanism. That means that when the mass of the fermion increases, because the coupling of the Higgs with the fermion also increases, the even in the limit, as this mass goes on increasing, the loop contributions do not fall down, and that is actually the point. And for the chiral fermions, they become almost independent in the limit of a very large mass of the heavy fermion. And therefore, this is a sort of parenthetical comment which will come later when you are discussing in the those days, in the discussion in the days to come. And I just wanted to show that for the known value of the Higgs mass now, the gamma-gamma width is actually proportional to AW plus A top square, which is dominated by the W contribution, because AW is about -7 and A top is about 1, which is about 0.2, that is quite a bit less than the W contribution. So these are just various facts that were used critically in evaluating the observation of the Higgs signal. And in the early days, when the top quark had not yet been discovered, and this I'm talking of really the early days, and when it was considered to be light, in fact, and this I'm talking around after, of course, the discovery of the charm quark. So that means, and the bottom quark, so 1974-75. For the heavier Higgs bosons, the dominant production mode was not GGH, but was rather the vector boson fusion and in the PP collisions. So anyway, when did everybody start taking the Higgs seriously? People started taking the Higgs particle very seriously when weak neutral current were discovered in 1974 at the predicted rates related to the weak charge current. And then there was a discovery of the CC bar resonance J psi at the right mass as predicted by Mary K. Gaia and Benjamin Lee from the observed K0 K0 bar mixing. Both of these supported the correctness of the gauge theory description of weak interactions. Luckily, by this time, the renormalizability of the spontaneously broken gauge theories was proved by 't Hooft and Weltman, which, if you remember in Weinberg's paper, was only assumed that it will be renormalizable. So all these three things together increase the belief in the gauge theoretic description of weak interaction, and spontaneous symmetry breaking was an ingredient, and the Higgs boson, as I told you, was a necessary ingredient of the gauge theoretic description. And the phenomenological study started from a very seminal paper called Profile of the Higgs Boson, which was written by Ellis, Mary K. Gaia, and Dimitri Nanopoulos in 1976. And again, I would reproduce something from the abstract to give you the feeling of what the early story was. The situation with regard to the Higgs boson is unsatisfactory. First, it should be stressed that they may not well exist. This is what I said earlier. Thus, the confirmation or exclusion of their existence would be an important constraint on gauge theory model building. Unfortunately, no way is known to calculate the mass of the Higgs boson, at least in the context of the popular Weinberg-Salam model. And here, this is called Weinberg-Salam model because Higgs didn't exist in the Weinberg-Salam, in Glasshow's model. So his mass, it's dependent on parameter lambda, which is not related at tree level to any other parameter in the standard model. So can just pure theoretical considerations tell us something about its mass? And this brings me to the most important thing, I'm running out of time, the high energy behavior of nu E bar going to W plus W minus, and E plus E minus going to W plus W minus that I talked earlier when I referred. And here one can show that if I just consider this T channel contribution, then this will be rise as energy S, but this gets exactly cancelled by the Z exchange diagram. And this happens only when the ZWW coupling has exactly the value that SU2L cross U1 gauge theory requires it to have. And in fact, the observation of the W plus W minus pair production at LEP2 and the behavior of the cross section with the energy, which flattens nicely with energy, proved the correctness of the ZWW coupling and proved the correctness of the SU2L cross U1 gauge structure. But mind you, this is still not the evidence of the Higgs, this by itself. This is evidence of a gauge theory where symmetry is spontaneously broken, but this is still not explicitly an evidence of the Higgs boson. In fact, in the case of nu bar to W plus W minus, only these two diagrams will contribute. For E plus E minus to W plus W minus, this additional diagram does contribute because of the very small mass of the Higgs, coupling of the mass of the electron with the Higgs. This actually numerically does not make any interesting contributions, but until and unless you include this contribution, you will actually get, if you just compute this, you will still get a leftover divergence where there is a very small numerical value, but it is proportional to the energy with logarithm, and that logarithmic violation of unitarity of this cross section actually gets cancelled exactly, restored exactly. Good high energy behavior is restored for E plus E minus going to W plus W minus through the Higgs exchange. But actually, it is this idea that this observation that can be taken further, and this was actually taken further by none other than John Bell, the great John Bell, of Bell's inequalities. And he actually showed that in the standard model, in the SU2L cross U1 gauge theory, which is spontaneously broken, with the couplings of the spontaneously broken gauge theory, if you compute all the scattering amplitudes, then each of these amplitudes taken by themselves have bad energy behavior and they grow like S or S square. But actually they cancel each other completely only if the couplings of the Z and the Higgs with the W pair are exactly as given in the standard model. If there exists heavy fermions, then you should also compute WW going to FF bar, for example. And that in that case, one finds that the cancellation happens only if the HFF bar couplings are exactly as in the standard model. In fact, this kind of tells us that there are perhaps, since Higgs gives the renormalizability to the standard model, this now tells us that perhaps there are deep relationships between unitarity and renormalizability. And in fact, Quick, Thacker, and Benjamin Lee noticed something very nice. I think this was sorry, I didn't write. This was a paper in 1974, I think. And they showed that the cancellation of the leading divergences of these diagrams is actually independent of the Higgs mass, which means existence of the Higgs is enough with the appropriate couplings is enough for this cancellation to happen. However, there is no dependency on the Higgs mass for the leading S to S and S square divergences. However, the WW going to WW amplitude has an image dependent piece, which is, this is not strictly only power dependence on the S, because this is S over S minus MH square, and this is T over T minus MH square. This will violate unitarity if MH is greater than this value, which is about 1000 GeV. A more correct calculation, keeping all the logarithms and so on, gave them the number in the paper, which was 780 GeV. Actually, somewhat simply, you can understand this also by realizing that for very large MH, the self-coupling lambda is large. So normally one said that at large MH, the Higgs has become strongly interacting, and that is where the violation of unitarity has begun. In fact, summary is the following, that demanding that W plus W minus scattering amplitude satisfy perturbative unitarity, one can actually derive the entire particle content of one generation of standard model. This was done by Tiktopoulos and Cornwall, and also by then a young theoretical particle physicist, Satish Joglekar, who was in fact a professor in IIT Kanpur, who passed away very early, tragically, last few years. And then Benjamin Lee and Thacker took over from there and showed that the perturbative unitarity is guaranteed only for if the Higgs mass is less than 780 GeV. So now this is the theoretical bound on the Higgs mass. So even though the theory cannot give you the mass of the Higgs, it tells you that if standard model with a point like Higgs has to be the right theory, tree-level perturbative unitarity tells you that MH is less than about a 1 TeV. Then there are additional bounds which are called triviality and stability bounds, which demand that the quartic coupling in the Higgs potential, which I had given, remains perturbative and positive under loop corrections. Now, these loop corrections in a quantum field theory will come from many particles in the theory. They will come from these self-interaction terms of the Higgses themselves, and they will come from the fermion loops. They will come from the vector boson loops. And at large MH and large lambda, remember MH and lambda are related. So at large MH and large lambda, actually what you can do, you can say that let me forget about all these and let me look at only these contributions to the running of the lambda. And then you can actually solve it rather trivially, and it takes this form. After looking at this, you realize that if Q square is very much greater than V square, then this lambda at Q square will actually develop a pole when this denominator goes to 0. So if you demand that lambda should always remain in the perturbative regime, we can then only have lambda equal to 0, and the theory will be trivial. It's a useless theory. One can actually take an alternative view. One can say that the scale at which small lambda blows up above a given scale capital lambda, that tells you that given scale, beyond a given scale lambda, standard model is no longer the right theory. And therefore, that would give a limit on the mass of the Higgs, because mass of the Higgs is related to lambda. So in fact, you find that the scale at which the pole lies, which is called lambda c, is given by this formula, which actually follows from this formula here. So if you say that the theory is valid, non-trivial, below 10 to the 16 GeV, we don't care what happened after 10 to the 16 GeV. This gives an upper bound on the Higgs mass, that is 200 GeV. This is called a triviality bound. So if we had found, for example, a Higgs which was bigger than 200 GeV, then we would have said, aha, we do know that this is an indication that there is new physics definitively beyond this scale. So just this mass of MH can give us an indication of the scale of new physics beyond the standard model. When MH is small and lambda is not large, then I cannot forget these loops. In fact, these loops I cannot forget. And in fact, for the heavy fermions, the top starts dominating the contributions. And in fact, now once again, you do the calculation, the top contributions dominate, the gauge boson contributions are there. In the early days, when the top was light, people only took these gauge boson contributions, and the top actually makes very interesting changes. And at small MH and hence small lambda v, at some value of Q, lambda actually can turn negative because of this large contribution, and the potential can become unbounded, vacuum can become unstable, and the condition for that the vacuum should not become unstable is this, which again tells you that if I want my theory standard model to be valid, let's say only up to 1000 GeV, and say there is new physics beyond 1000 GeV, then the Higgs mass should be greater than 70 GeV. So theoretical considerations of stability as well as triviality bound the Higgs mass from below as well as from above. Actually, the earliest calculations of stability bounds were done independently by Linde and Weinberg. This is a paper by Weinberg in 1975, and it says that the stability of the vacuum sets a lower bound on the Higgs boson mass, and for the simplest model, the lower bound is about 3.72 GeV, clearly because he didn't have heavy fermions in his theory, and he did not know what the masses of the W and the Z bosons were. So, and then he said, actually, this is typical of Weinberg. If the light Higgs boson has a mass of the order of 5 to 10 GeV, the best place to produce may be in a neutrino reaction. Then he says that he has talked with Mr. Mann, who was a neutrino physicist. And then he says for in a neutrino reaction, such a Higgs would tend to be emitted from the exchange intermediate vector boson line, and the probability of producing the Higgs boson then would be of the order of GF time E square. See, he already sees the importance of experimental verification. And as you, this is where I said I will weave in my own own sort of involvement in this. And this is my perhaps the second paper in my PhD thesis, and where at that time there were some unexplained trimuon events that were found in neutrino reactions, and yours truly had indeed calculated the emission of the Higgs boson line from the W line and then decaying into a mu plus mu minus. The events did not show the characteristic that was expected for the Higgs boson, and therefore we had to only conclude that the trimuon events were not due to the Higgs production. But this was actually telling you in how, in which ways one started looking for the Higgs boson. Now I jump many decades, and I produce a paper from a paper of Elis Giudice, the theoretical bounds, in a paper of 2009. And the formulae that I gave you were tree-level formulae. They did higher order correction calculations. They also have the Tevatron limits from direct searches, and which I'm sure that some of his Vivek will talk about. Then the LEP searches. So if you forget about these gray regions, then these are the pure theoretical bounds, upper bound as well as the lower bounds that are implied from the standard model at that time, using the known physics that was in the 2009, where we knew the masses of the W, we knew the mass of the top. So the task that was set to the LHC in 1980, I would say in 1986, this was not so clear. So in 1986, the task that was set to the LHC was to find a Higgs in this vast mass range. This 70 would actually be smaller because with the known mass of the top in 86, actually in the first studies, a lot of attention was actually focused on the VBF production. And in fact, the famous boosted jets idea, I want to tell this to young experimentalists, was suggested by Butterworth and his collaborators to reduce the QCD background for the heavy Higgs searches, when the heavy Higgs will only decay into W plus W minus. And there were two reasons why many people had focused on VBF production in the early papers. One was that the GGH rates were not promising because the top loop contribution in the GGH was rather small. And for the heavier Higgses, therefore, the WW fusion was much larger cross sections. And if they become really heavy, that strongly interacting, then the WW dynamics would have had important information about the symmetry breaking. So in that sense, LHC was a no-lose machine. You either find it in the gluon fusion channel or you find it in the WW channel. And that is what actually was emphasized in the 1986 yellow reports. And as I said, there was a lot of discussion of the VBF mechanism. One did not quite have actually at that time the MAD graph and the MAD event generators. And many of us phenomenologists actually wrote our own programs to calculate mod M square and then shared them with the experimentalists. And full QQ going to WW going to H calculation was done by Chanovitz et al. But people, and I would say some among them were myself and Saurabh Bindani, we also used it to study it in the effective W approximation, which are now making a comeback in the context of newer discussions when we start talking of mu plus mu minus colliders. So the Higgs hunters, actually, one of the authors of the guide will speak later in the conference, adapted their tools as they had a better idea where to hunt. And between 1986 and 2007, a lot of water flown under the bridge, and we knew much more about the Higgs mass using the theory as well as the precision measurement. So now I want to come the last few minutes of my talk, like 2 minutes actually that I'm left with. Seema, can I take 5 more minutes?
Yes, but 5 only.
Yeah, no,
so that we can have a couple of questions.
Overran.
Yeah,
so
yeah,
at tree level, the mass of the Higgs mass was, since MH is not related to any other parameters, but we know that SM is a gauge field theory and quantum corrections link different parameters. And the corrections due to loops containing a Higgs can modify the W and Z masses. So you can get indirect information of Higgs mass and MW. You can get indirection of the information on Higgs mass from the measured masses of the W, Z, and the top. And that is here I have tried to explain, but I will skip this part. The corrections for the W and Z are different, as you can see in these diagrams, because Z and W have different particles in the loops, and therefore the rho, which was defined as mz square, mw square over mz square cos square theta w, will change away from the tree level value of 1. And from the corrections, you can actually get first the measure of top mass. And once you measure, it does depend on the Higgs mass, but only logarithmically. But once you know the top mass, you can actually get information about the Higgs mass too. So the logical steps in precision testing of the standard model is the following. Standard model has 3 parameters, G1, G2, and V. All the SM couplings, gauge boson masses are functions of this. A large number of electroweak observables were measured at lab very accurately, and MZ and alpha EM and G mu were most accurately measured. So trade G1, G2, and V for these. And then, of course, they depend on MF, MH, and alpha S, MF and MH through loop corrections. Calculate all observables using one loop electroweak radiative corrections, compare with data, make the standard model fit, test the standard model at loop level. This is what lab did. But more importantly, what it does, it also gives us indirect information about the Higgs mass as well. And this is in 2011, the dawn of Higgs discovery, I would call. It said that from the precision measurement at lab, we knew that the Higgs mass in the standard model should be less than 160 GeV. And these gray bands are again the regions that were removed by the experimental searches. Again, something that I'm hoping Vivek will cover. So literally on the eve of the Higgs discovery, that is March 2012, actually Tevatron came up with a very nice measurement of MW. And what happened is that now you look at, by this time, LHC had also excluded a fair region of the Higgs masses. And then what was left was this green here, okay, which was allowed by LHC searches and which was consistent with the MW and the MTOF measurements. So in the standard model, the Higgs was to lie in this green slither, and indeed a better presentation in can be seen here, that compare the fit, all the indirect and the direct experimental searches for the Higgs said that the Higgs should be now lying in March 2012 in this white region. How do I, when I compare it with the confluence of the direct, indirect, and the theoretical limits, you find that the only region that was consistent with all the constraints was here, the value of the MH. So now one begins to see that most likely standard model is correct all the way to Planck scale perhaps. So the allowed Higgs mass range was restricted to a very narrow range with all the different constraints. Direct experimental searches, indirect experimental constraints, using theory of course, and pure theoretical constraints. So if the Higgs had not been discovered 10 years ago, which we are celebrating, where it was, perhaps it would have been even more fun. But the relief of all of us who lived through the 4 decades from 74 to 2012, LHC did find Higgs in that narrow slither. It gave the final confirmation of the correctness of the model of leptons. This was triumph of gauge principles and spontaneous symmetry breaking. You will hear the story of this discovery and of course much, much more about how one can use this Higgs now as a tool to probe physics beyond the standard model, now that we have proved the standard model. And I think thousands have contributed in many ways over decades, not just the experimentalists, not just the accelerator physicists, and not just the detector builders, but also a hell of a lot of theorists. And my purpose was to show you this mixture of theory and experiments, how that has guided us in the study of the Higgs physics. Wish you a lot of enjoyment in the conference, and I will stop sharing it.
Thank you very much, Rohini, for this interesting talk and taking us through this interesting journey of developing these ideas for the Higgs boson. So we can take a few quick questions. I see Nishita, hands up. Yes,
Thank
please
you so
go ahead.
much
Yeah.
Thank you so much for the very nice history. So I actually have again a historical question. So we are getting questions now about discoveries at the LHC and why it is not making any new discoveries. So I was wondering what you remember about LEP, because LEP did, of course, make very precise measurements, but there was no big discovery at the time. And not finding the Higgs, how did people take it at that time?
Actually, I think at that time, LHC was already on the horizon. No? So people were not too unhappy, to be honest. I mean, it gave actually LHC's raison d'être, no? I mean,
Right.
So I don't think sociologically people were unhappy. Of course, quite a few felt that could we have not run ILEP a little longer
Right.
and known much earlier, perhaps. But by this time, LHC had progressed, and then there were big discussions about whether the few magnets should be added and LEP energy should be increased. Because if you remember, the LEP limit is 114 GeV on the Higgs mass. And also
there
the
was
point,
an excess, right?
huh?
There was a small 2 sigma excess at the very edge.
Yeah. But that is, I think the usual excesses at the end of the kinematic reach. But the point that I would actually like to make is that the reason LEP could see Higgs to much higher masses is because the TT bar background was absent, because the top was so heavy. That was something not known when even LEP was designed or LHC was designed. It's all, that was part of the reason that the absence of the background coming from TT bar actually allowed people to push the LEP limit to much beyond. Otherwise, E plus E minus going to HZ sort of would have said that the maximum you can push is root S minus, MZ, I forget this now, root S minus MZ minus 10, something like that. That was the MH limit, roughly. And that is what it actually came. That was the kinematic limit for the cross section.
Okay, we have question from our host meeting room. TFR, please. I think you are muted. Yeah, we can hear you now.
Okay, thank you. No, I didn't log in, so I wanted to. So this is more on the, Rohini, you showed that plot where you had the theory and experimental bounds, the direct bounds, and then the unitarity and triviality, all that you said. Maybe, anyway, I think you don't have to go to that slide. So the question I was trying to make, the very nice way you explained that how experiment and theory have gone hand in hand to arrive, where we are with the Higgs physics expert. So what is your feeling? I mean, looking ahead, like let's say we're talking of the celebrating the Higgs, but then I'm looking ahead. Would you say that we haven't had that much of in the experimental side? Because right now from the theory side, I mean, we have many models, right? But what you showed, there's a very beautiful story, like there's certain experimental observation, and then people come up with the idea that, okay, this should be this and this should be this, and then things slowly piled up and we are here where we are. But going beyond the Higgs, I mean, sort of going for the physics beyond standard model, somehow my feeling is that has not yet happened. Would you sort of say that on the...
Well, I would actually beg to differ with you, Gagan. I mean, indeed, I agree with you that this I have said very often in my talks, which you have heard before, is that it is now the stage of the experiments to produce something interesting, okay?
Yeah.
But actually, my point is that the point that I wanted to bring here also was that, now we have to, in my mind, such interesting things are being thrown out by experiments in the Bay physics sector now. Okay. And, the kind of results that are coming from LHCb, or G-2. And now actually, I think the whole point is again, that the game is actually open. And in fact, I think we will have discussions on studying the Higgs sector also in these effective field theory techniques.
Mhm.
So maybe we are going back to go to the time when we have to take effective field theories as a technique.
Sure.
Okay. And of course, the space of parameters is huge.
Right.
And, we had a gauge principle or the chiral fermion principle, which directed us. Now, we don't seem to have an obvious principle.
Okay.
Supersymmetry was that principle we all thought.
Mhm.
And we all still haven't found any evidence for it. But at the same time, again,
Nothing
just like the Higgs mass, let me complete here. Just like the Higgs mass cannot be predicted, the scale of supersymmetry also cannot be predicted. And that is why the principle, one beautiful principle that we have, is not able to guide us, at least in the high energy searches. But I think in my mind, right now, looking at indirect effects of new physics in the Higgs, through the Higgs portal, through G-2, through B physics, or through W mass, for all I know. Okay. So
Yeah.
maybe the
So-
more
Actually, this
traditional-
discussion will be more apt towards the end of this workshop, I would say. When we
Yeah,
can
I-
talk of
I-
everything.
I-
So I think we should move ahead. If
Yeah. No, that's perfectly fine. I was just trying to say that from the experimental side, if there is any specific thing, I think he answered that. Basically, what is that we need to do better so that it helps
precision
into the
measurements,
thing. So
precision
more to that-
measurements, even at the LHC.
Yeah, I think
Measure
that-
the top quark coupling
yeah,
precisely,
so-
measure the Higgs couplings precisely.
Yeah. Okay. Thank you.
okay, so I think we need to move ahead unless it is very urgent question.